my previous class. So last day we stopped that the distribution of the electron or the quantum number of a atomic system. So as per the if you consider the hydrogen-like atom or the Bohr formula, then you can consider that n equal to 1, where n should be 0, and n equal to 2, L should be 0 and 1, and n equal to 3, L should be 0, 1, 2. N equal to 4, L should be 0, 1, 2, and 3. So this distribution is n. If n is your quantum number, then angular quantum number should be n minus 1, n minus 2, and so on up to 0. That is the distribution of these types of quantum number you will get. Here for what does mean L equal to 0? L equal to 0 correspond to your s orbital, and for L equal to 1 it's correspond to p orbital. L equal to 2 correspond to d orbital, and L equal to 3 correspond to f orbital. You know. Now under magnetic field, what will happen? This angular momentum will exist because due to the rotations of the, if you it's any charge particle rotate around this, so you should have some this angular momentum. Now this angular momentum can under magnetic field can be distributed. If we apply some magnetic field for each of these quantum number, it can change to ml value, azimuthal quantum number. For L equal to 1, if it is L equal to 1, ml should be plus minus 1, 0. That means it should be, in general, it should be, ml should be plus minus L, plus minus L minus 1, plus minus L minus 2, up to 0. This is the ml value in general. So what is happening in this case, if you have some momentum, this any charged particle moving around a circular path, it should create some magnetic field. So it's clockwise or anti-clockwise, depending on if it is the anti-clockwise, the direction of the magnetic field it's produced should be something like, if it's moving anti-clockwise, if it's moving a clockwise, then this should be this direction. So you have some magnetic field, any charged particle moving around the circular path or flowing of the current, flow of the current will produce some magnetic field. So that you will get it. So under, if we apply some magnetic field now, then it can distribute its direction. So some discrete direction it can go. If L equal, depending on this L value, the plus L plus, if we say this is plus L, then it should be plus minus L minus 1 and so on to 0, means plus this side, then it should be L minus 1, and then it should be L plus L. So this is the magnitude. Total L should remain same, magnitude should remain same. This way you can get the distribution. So ml value for L equal to 1, if you got for L equal to 0, ml is 0. L equal to 1, ml value should be 1, 0, minus 1. For L equal to 2, ml value should be 2, 1, 0, minus 1, minus 2, and so on. Now for each of these ml value, if we consider for n equal to 1, if I now want to break it, for n equal to 1, you have L value is 0, ml value is 0. N equal to 2, you have the, now if you consider for L value is 0. L value is 0 and L value is 1. This is two part, L equal to 0 and L equal to 1. So L equal to 0, ml equal to 0, then if I separate this orbit, So discretize this one. Now L equal to 1. For each ml value, now we have 3 ml value. 1, if I say 1, 0, minus 1. This is the process. Now, if n equal to 3, you have the another part will come. N equal to 3, if I consider, then your L value is 0, L value is 1, and another L value should be, if I think its L value is 2. So now with this ml value for this 0, now we have 3 ml value here, same m equal to, this is ml is 1, if I say 1, 0, minus 1, 1, and how many signature you got? Only? Yes, sir. और कोई नहीं है? Only one J. अजय देव? नहीं सर, अजय देव सर भी है नहीं हो. अजय वैसा? अजय वैसा कर देंगे. ठीक है, तब मान लो. For email value, this should be 2, 1, 0, minus 1, minus 2. Now the another important part, what will come? Now this is the orbital n 1, 2, 3. The principal quantum number n, L is the angular momentum number, ml is the azimuthal quantum number. Now you consider that each of this, you don't know this part. Still, I want to explain to that. Each this earlier, I also explained what does it mean by spin. The electron can move its own axis. If we assume something like this, if it's rotate in some direction, is clockwise direction, you have the spin up. If you have anti-clockwise, then spin up. If it's rotate its own axis around the clockwise direction, we may assume something like this. Then it's a spin down, and the magnitude of all this plus minus half h curve. This is plus and this is minus half h curve. This is the value magnitude of the magnetic moment of this spin. So now each of these ml now under magnet due to this rotation, each of the states can accommodate 2 electrons. One should be spin up, one should be spin down. One should be spin up, one should be spin down. Then each of this box you can fill now something like this. This way it can fill the electronic level. So depend on this. Up, down, up, down. So here. So now here 2 electron, here 6 electron, here 10 electron is there. If the next level n equal to 4, you can find the other electron that you can get the 7 means 14 electron for the A orbit. Now you can distribute this this system. It looks very blunt, so I have to magnify. So this is the order or of this distribution of the all quantum number. Now we can apply, we can generate the systematic plot of just 2 minutes. Again, we will start from the one inside. So now you can consider the orbit. This is the nucleus, and now you can consider this is n equal to 1. This is the n equal to 2, and then you have these are the principal quantum number, n equal to 3 and higher order. Now, as per the electronic distribution, you consider the one at one system hydrogen. Hydrogen Z value is 1. So 1 electron inside, 1 positive charge inside. Of course, the neutron is there, another neutron. Then the negative charge electron, only 1. So it could be here. So it will fill in 1. You can write the energetical distribution n equal to 1. This n equal to 1 value is 1. With energy, you can space only L value is also 0. So you have only one system. ML also 0. So energetically, this should be this order. This is lowest. Here you have the one spin up, spin down. if you give the magnetic field, this ml value will split into two energy level. One should accommodate the spin up, another should be spin down. So this way, this should be under magnet, it can split. So n equal to 2, if you consider n equal to 2, you have L value. N equal to 2 energy level is here in general. Now, and this level. Now L equal to 2 means you have two systems. One is here L value. L equal to 0 and equal to 1. Under magnetic field, now it can split into ml value. So this one will 3 energy level ml value -1, 0, +1. This one, and this L will remain here. So now this single quantum number, this energy level orbit now splitted under magnetic field into this ml value. So you can spike each of these now under magnetic field can accommodate 2 electrons due to this spin up, spin down. So each will split into 2 levels under magnetic field. So each of these electron distribution should, if you have one electron, only ground state should be filled up. Only ground state should fill up. You have two electron, ground state and the upper one also. This should be fill up, spin down, both will fill this n equal to 1. If n equal to, you have the Z number is 1, so only electron. It could be spin up down in the only one level should be there. If Z equal to 2, that is a helium. So this two part will fill. So it's the self-filling. This will complete this Z equal to 2. If we have other value, Z is 3. Then 2 electron goes to here, another electron will reach to this level. S is 2s. This is now 1s, both is filled. Now 2s1, so 2s1 should fill. If Z equal to 4, then this two level will fill. Then the other level, this way you can distribute this your electron level. So atom Z value change. So how this electron should distribute it? From here you can go for n equal to 3. You can energetically check n equal to 3. You have this level. So n equal to 3 means L value is you have to discretize L value. L is 0. Then L equal to 1. Then your L equal to 2. L value this one. Now L equal to 0 is ml value. If you want to discretize ml value under magnetic field, it's ml. The azimuthal quantum number will generate. So this is remain this L equal to 0. L equal to 1 create 3 level. L equal to the ml value -1, 0, 1. Then L equal to 2 will generate 5 level 0, -1, -1, -2, and 1 + 2. Now under if spin system, so each can accommodate 2 electrons, so that should be the ms value, spin level degeneracy. It should be in 2 level, and so on. This should be your electronic distribution, each of these. So n equal to 2 can n equal to 1 contain 2 electron total maximum. N equal to 2 can contain 2s2 plus 2p6, 6 electron. So 8 electron can accommodate here. Here 3s2, then 3p6, and then 3d10. So 10. So 2, 6, 10. So this is your 18 electron can accommodate n equal to 3 level. 18 electron can accommodate in this way. So this is the your electronic distribution of this atom. Let's one of the material I am talking about, silicon. Silicon electron number is 14. Number Z electron number of electron is 14. So distribution is 1s2, 2s2, 2p, 2p6, 3s2, and 3p2. This is the distribution 2, 8, 10, 2 to 4. This electron number. So how they will fill energetically? First lower level will fill. So 2, then 2, 6. This is fill. Then this 2 level, then p6 of 2 is now filled. So this is the electronic distribution in this different orbit. Now energetically you are checking energetically, if you consider energetically that now it is one of atom of silicon I am drawing. So this is, let's assume 1s2. 2 electron is there. Spin up, spin down. Then you have this energy level. Here you have this 2s2. So 2 electron here and 2p6, 6 electronic level. So should fill. Now last orbit you have 3s2 and 3p2, 2 electron. So it is something like this. Electron is there. 2 electrons should fill this level and 2 electron can fill this level, and then the other 2 levels should be vacant. Now this drawing you should keep in mind, this is energetically, this is close to the nucleus. So this is deeper energy. If you want to remove electron from 1s level, so you need higher energy up to the vacuum. This is higher energy, this is deeper energy. This is lower energy. If you want to remove this electron from here, you need lower energy. From here, if you want to remove, you need higher energy. It means lower energy. This is close to nucleus. This atom this electron is attracted very strongly. So removal of the electron from this 1s level of silicon is very difficult. You need very high energy of the order of, I think, around 100 electrovolt. These are slow. This one from this outer level, if you want to remove the electron on of the order of around 4 electrovolt. So these are very close to, means outside to the this is far away from the nucleus. Binding is low. So if you consider orbit, if I want to this radius of this small, so if, as per this drawing, radius is smaller, it's the higher energy. So if you other orbit, your radius should be bigger. So the upper orbit should be again bigger radius. This is the concept of the atom, pure atom. If you consider, this is the situation. Now I want to say what will happen if you make two atoms close to each other. Let's assume a hydrogenic system, only one hydrogen atom. You consider this level. This is isolated hydrogen atom, 1s2, 1s2. This is level, but one electron is only there. So this is the hydrogen. But feasibly, it can this level can accommodate only 2 electron maximum. One is there, but it can accommodate 2 electron. Now, if assume you are making hydrogen molecule, H2 molecule, then what will happen? That means in the molecular case, these two orbit should overlap. This orbit, the interaction orbit of this radius of this orbit will overlap of this orbit. This is the, I'm making it closer to here. This is the hydrogen molecule. So now you check the both orbit of the H1 atom, first atom, and H2 atom now overlap. Now, if they are isolated to each other, what will happen? Their energy level, this should be 13.6 electrovolt minus 13.6 eV, and same this one should be minus 13.6 electrovolt. Now check when they overlap to each other. This level can accommodate 2 electron, and this hydrogen atom also accommodate 2 electron. If they overlap, their energy earlier remains same. So that means they overlap their energy level, both can same energy level. If this one can accommodate 2 electron, this one can accommodate 2 electron. Now this system can accommodate 4 electron. It is against the Pauli exclusion principle. Against the Pauli exclusion principle. If it's against the Pauli exclusion principle, that means this is not feasible condition. It will never happen. So in as per this distribution, that each ml value can only accommodate 2 electron, not more than that. Now you have both this ml value have the two hydrogen atoms, separate atom, two atom can accommodate two individual electrons. So this one can accommodate two electrons. This one can also accommodate two electrons. That means if you couple it, same energy level can accommodate four electrons. But this is against the law. It's not possible. Same electron, if ml level is same, then never it cannot accommodate more than two electrons. So no energy level should have the more than one quantum number. So if we break its spin number, so it's not possible to accommodate more than two electrons. So four electrons, it's not possible. So then what will happen? They will interact, they will fight to each other. Simply, if I say you have two chair, two chair, someone you have to occupy, someone should, you have to, one is here, another is this one. So you have two level. Otherwise, one have to go to lower energy, lower one, other one should go to upper. So you have to fight to each other. So here, electron will fight to each other somehow. What will happen? And one energy level, if this is your initial 13.6 electrovolt or energy level from the vacuum level of reference, vacuum level, then two electrons may accommodate this lower level and other two can go to the upper level. This splitting will happen equally from this reference level, delta above, delta low. This lower energy we call the bonding energy level, bonding state or bonding energy level, bonding states, and upper one is the anti-bonding. This must happen. So otherwise, they will violate the basic principle. In nature, what is happening? In nature, this electron, if what is happening, that the outermost electron of this two atom, if I say this is nucleus, this is one electron is here, this one electron is here, this is electron, this electron and this electron. Initially, you are only counting this interaction of this nucleus and the Bohr model. You consider this potential Z square by R. This one is constant term, so it's a attractive potential. Now you consider here what is your potential. This is Z square by R for this one and this one, 2 Z square by R plus E square by this is repulsive. This electron and this electron will repel each other. Coulomb repulsion. Two positive, two negative charge can repel each other depending on their distance. If I say this R1 E to E, if I say this distance, so then you have the interaction should be E square divided by some this constant, this 1 E 2 E. This is the potential, additional potential. Another potential, this nucleus and this nucleus will interact to each other, then you have another repulsive potential. This Z value, what about this Z? If you consider Z square is square by, if this nuclear distance is R1n and 2n, if I say R1n and 1n, 2n, so into constant. This should be the total potential. Due to this addition of this potential in the energy calculation, you will find the splitting. So in just term of the Pauli exclusion principle, if you consider, you can get that's not possible. But how if you quantify this value, then you have to add this potential in your solution, and then you can find how much this. If you know this distance between this nucleus and this one average distance, then you can able to calculate this splitting. Closer is the distance, closer should be the splitting should be higher. So two electronic level will split each other due to the Pauli exclusion principle, and also how it's happening. If you want to quantify, then you have to consider this additional potential. So Coulomb repulsion potential is responsible for this types of splitting. So one should go to the lower energy level, another should go to the upper energy level. Lower energy level we call the bonding state, upper energy level we call the anti-bonding state. So this is the molecular information of the state. All other upper level, they are also will split into, each level will split into two level if their orbit is overlapping to each other. If you have somehow assume that three level will interact, three atoms somehow are possible to interact. So this single energy level will split into three energy level. If it's four atom, it will split into four energy level. So this way the splitting will occur in the molecule. So now if you consider this our silicon atom, what is happening? In silicon atom, now you are considered this is the isolated silicon. We initially consider this isolated silicon atom, and so on. Linear chain you can take. Okay, it's too high. Something I am drawing, tentative idea. So maybe this is 1s. This is the orbit of 1s, 2. Then you have 2 electron, all this orbit is there. Now you have the 2s, 2p here, 2s, 2s, 2p is there. So let's just simply we consider here energetically they are there. Energy measurement is from here, from the vacuum level. You can measure. This is the 1s level. This is 2s, 2p level. You can consider 2 level is here. Now the upper level is you have 3s, 3p level. So you have 2 energy split. Of course, splitting you know that how many electron now. So orbit wise is simplified this energy level. Is 1. This is the part. If they are not interacting in the, if all silicon atom is far away to each other, so I just draw it here, this overlapping. So initially I don't want to consider this overlapping. If they are not interacting, so they are not overlap. These orbit are not overlap. They are isolated. So it's not interacting. Now if you consider, now you want to make it closer, the distance between this atom, you are now making this distance, you are making closer to each other. What will happen? These are the bigger orbit. These orbit are bigger. If you make it closer, then what will happen? Their orbit should overlap. This, if you draw it close to each other, if you draw it, you are making closer to each other. And so on. This part, lower part, 1s level, they will not interact because they are smaller orbit. This one also most likely they will not overlap to each other. 2s, 2p level, 2p level, they will not overlap to each other. But the 3s3p, the outermost level, 3s3p, they will overlap to each other. The outermost cell in general we call is the valence orbit or valence electron. We call valence. If they overlap, now we consider this level 2s2p level, they will split to each other. They will split due to this. So this number of atom will split. This how many silicon are there? They are interacting. They will split in that level. So this is the physics of the interacting part. Now if you in number of atom I am consider, they will be lower part, they should be isolated. 1s level should be isolated, 2s should be isolated, but 2s, 2p, they are isolated because their orbit is smaller. But initially, this the upper orbit, the valence orbit, they will overlap. You make it closer to each other, they will try to overlap. And overlapping means orbit overlapping means energetically they are interacting. That means this electron can move from it is overlapping means electron can go to this side. This is the meaning of the overlapping. And the other way, if you can think that the Pauli exclusion principle or the due to the electron interaction, this state will split. Now initially, if I consider distance between the silicon atom is high. If you have any queries, you can stop me anywhere. If I say infinity, so in silicon, solid silicon, how many electrons are there? Do you have any idea? If I consider 1 centimeter cube of a silicon material, how many atoms should be there? Do you have any idea? It should be Avogadro number. So order is 6 point something into 10 to the power 23 per centimeter cube. This is the number. So in per centimeter cube, 10 to the power 23 number of silicon atoms should be there. So then what will happen? So if they are not interacting. So if silicon atom, this 10 to the power 23 silicon atom, if I say Na or n number of atom, so if we consider this n number of atom, they are no interaction. Electron are not interacting. This R value, the nucleus of this one atom to the other atom is far away. Let's assume infinity. So then each energy level should remain isolated. So all this energy level, one is level should remain as it is. So this should be filled by two electrons. So each. Now n number of atoms. So if I say this is 2n number of electronic state is there, by excluding the spin degeneration we remove. So 2n number of state is there, and all are in same energy level. This 2n number of this one is level, that 2n number of energy level will remain as it is. That means this energetically this one remain as it is, no interaction. All are in same energy of silicon ground state, one is level, no interaction, no change. All are in the same energy level. So we in general, in terms of physics, we call this degenerate state. Degenerate states. If in the same energy, if we have multiple number of states, we call the degenerate level. If we have n number of same energy level, so ground state energy, so you have n number of states, so all are in same energy, so we call degenerate states. Degeneracy is 2n. Now you consider the other level, the second level, that 2n, same 2n number of electrons should fill this state. So these are the number of state, all are same energy. Now here you have 2p6. So here how many states is there? 6 into n, 6n state for electron. All are infinite. Now you have this one. If I say 3s2, 3p2, 2 electrons are there. So now you can check 3s2, 2n is electron here, electronic state, and here you have 4n state, 4n states, a 6n state. This is 2 electrons are there, but you have the 6n state is there. These are the states number. Now fill, how many states are filled state? Filled state. Writing, it's vibrating, so writing is a little difficult. So now the field state, if I say field state is here. You, from the lower state you can consider how many states are field state. So ground state you can consider that 2n all states are filled, lower part. This 2n also filled, this 6n also filled. Here 2n is filled for silicon distribution. I explained you earlier, 1s2, 2s2, 2p6, then 3s2 and 3p2. So these 6n state are available, but 2n are filled state. If what happened now, if you now reduce this energy level, now you try to reduce this R value, in infinity, no interaction, nothing will happen. So this state all should be degenerate state. All silicon have the individual identity, they will remain there. But if you reduce this R value, infinity, so this part remains same, this part remains same, no change. This part remains same, this degenerates because they will not overlap its silicon atomic case. But here what will happen if you try to reduce this 2n state under this interaction, if they have some interaction, they will start to split into 2n energy level. 2n energy level, they will split to each other. This one, how many? They will 6n state, 6n state, they will split into 6n state. 6n, this one 2n, they will split into 2n state. So if you reduce this size, this part is moving up and lower, this one moving up and down both way. So somewhere you can find this all state will overlap. So now you can situation somewhere you can find 8n state. Here you can check this 2n state, all electrons are filled state, so 2n are the filled electron. Here 6n state, but 2n are filled electron. 4n are vacant. Here in this region, if you check, 4n electron are there, so 2n, 2n, 4n are filled state and 4n are vacant. If you further reduce this distance between this atom, then what will happen? Due to this attraction and repulsion, both will play a role. What will happen? Something happen in between some distance, somewhere. Two splitting will occur. Two band splitting will occur. Some state will go to this way with distance. If you consider somewhere, this is the one band. This is another band. This contains 4n states. This contains 4n states. This is states, 4n state. And in between you have some gap. This gap is called forbidden energy gap. Forbidden gap, energy gap, energy gap. So that means nothing is there. So no electronic state is there. That means no electron can sit in this region. So energy of this electron should have lower or upper. In between, no energy is possible. Electron cannot have any energy. So now you can see this lower level, 4n state, this higher level is 4n state. Now this 4n electron you have, so all will try to fill in lowest temperature. If you consider lowest temperature, that each electron can sit one of these electronic level, 4n electron are available, so this 4n state should be filled at 0 Kelvin temperature, let's assume. And this 4n state should be vacant state. This 4n upper state we call the conduction band. This 4n upper state we call the conduction band. And the lower part we call these states are fully filled by this electron, we call the valence band. So physically the valence electron now split into two groups. One group have lower energy where electrons are occupied, that called the valence band. The upper energy level, that is called the conduction band. And in between the valence and conduction band, you have some forbidden energy gap. For silicon, this gap is 1.1 electron-volt. For silicon, this forbidden gap is 1.1 electron-volt. For germanium, for this gap Eg, now if you quantify this one, this major gap, for silicon is 1. For silicon it is, if I write it, silicon 1.1 electron-volt. For germanium this gap is 0.7 electron-volt. For gallium arsenide, it's a compound semiconductor, this gap is 1.4 electron-volt. Zinc oxide, ZnO, this gap is around 3.9 electron-volt. If we consider SiO2, silicon oxide, this gap is 9.1 electron-volt. If it's silicon carbide, SiC, then this gap is around 3.9 electron-volt. Silicon nitride, Si3N4, silicon nitride, this gap is 5.5 electron-volt. So and so on. The important thing now on to this is the gap is very important. This gap we can consider this one. So if you consider this gap is very important, this upper band valence electron, outermost shell electron in the solid form, means when they are close to each other, can split into two bands. Why we call this band? Because this band contains 4n electron. But these are also all are discrete energy level, 4 and discrete energy level. But the energy difference between two consecutive energy level inside the band is very, very small. This gap is delta E. If we consider within the band, this energy difference is in solid. In general, it is of the order of femto electrovolt. 1 femto electrovolt means 10 to the power minus 15 electrovolt. This is the order of magnitude where the forbidden gap is of the order of 1 electrovolt. So you can consider this 10 to the power 15 times higher this gap is. So now you can consider another important thing. If we measure the thermal energy, room temperature energy, if we measure the room temperature, see 25 Kelvin temperature, what is the measurement scale of this? 25 Kelvin means in room temperature, at the rate of room temperature, this 300 Kelvin means 25.8 millielectron. So if you consider room temperature energy is far, far higher this energy level, this discrete energy level, it's far, far higher than this energy level. That means if we have somehow electron are there, so it can cross anyhow this order of magnitude. If you consider this energy level is staircase, this consider your room, your home staircase, this energy level. This is femtoelectrovolt level. So this staircase. But your energy, room temperature energy, what you are gaining from the electron, if you are in room temperature, energy is 10 to the power, this millielectrovolt, 10 to the power minus 3 electrovolt. So order of difference is this higher. This how much higher? 10 to the power 12 times higher. 10 to the power 12 times higher. Room temperature energy is higher, 10 to the power 12 times higher than this. The successive energy difference between the gap in the conduction or valence band. So that's why it's very high. So if you compare this is it's the earth. If you consider this is earth and your home staircase this one and this is your sky. So energy kVt is now kVt is around sky limit. So electron, if this energy is, so it cannot see, this electron cannot see this energy level. So it can easily cross any energy level. So that's why the magnitude wise it is very high. So if you reach one of these band, the electron can move any of this energy system. So if I simplify and schematically draw this the upper level, this the valence part of the system. This is if I say conduction band, this is I say valence band. So you have discrete level and it have the end, and this is higher number. This energy difference is very small, but this gap is very high. This is the EG we call the forbidden energy gap or energy gap in simplicity. So electron in lowest temperature, these are field state. All electrons should occupy this in the valence band, and conduction band are completely unfilled. This is vacant state. These are vacant at 0 Kelvin temperature. At 0 Kelvin temperature. Now, if we increase the temperature, what will happen? If we increase the temperature, now electron can gain energy from this and it can reach to here. Following a statistic, we call it FD statistic, Fermi-Dirac statistics for electron. You can learn why it means Fermi-Dirac. Two types of statistics there: Fermi-Dirac statistics, statistics. We have this is called FD statistics. FD statistics. It's called Fermi-Dirac statistics. This particle is the call who follow the Fermi-Dirac statistics. We call fermions. Another types of statistic is Bose-Einstein. We call BE statistics. That follow we call the boson. Boson is the name Bose come. So SN Bose, Satyendranath Bose. E for Einstein is called bosons. Bosons, two types of particle where the spin of the particle FD statistics, we call that we measure the spin. It could be odd integer. This half integer. In terms of half 3 by 2, etc. If the spin value is half of 3 by 2, 5 by 2, if those particles follow or the half integer spin, then we follow the Bose FD statistic. If those have the 1, 2, 3, etc. integer multiples participate, those follow the Bose statistic. So this will follow some statistics for if the statistic distribution of the statistic. If your the particle have energy this one, you have to follow something like this: E minus EF. F is the Fermi energy level or the chemical potential of the system. And Kb is the Planck Kb is the Boltzmann constant, and T is your the room temperature. E is the energy of the particle and minus EF. This distribution, if you check from this distribution, you can understand that if you have some energy E, so from that electron can reach to some of this level. So if you increase the temperature, then the electron can reach from here to here. Some electron can reach of this from this valence band. Then you can consider here some vacant state. Electron keep go from conduction valence band to the conduction band. Then one vacancy of electron will be created. This is called positive. This will behave like a absent of electron, that is purely positive charge. So this is called hole. And who reach to the conduction band? Those are electron. This gap system, semiconductor system, if you increase the temperature, some of this electron can move from valence band to the conduction band. So it creates electron and hole here. So it called EH pair, electron hole pair can be generated. Electron hole pair can be generated at a time. So if you increase the temperature in semiconductor, electron hole pair will be generated. And if you increase further, number of electron hole pair should be high. Another important thing I have to mention, if electron reach to the conduction band, then only they should be available for the transportation. If electron are valence band, it will not participate in the transportation. They are strongly bound to the nucleus of this individual atom. If they have higher energy, that means in the conduction band, then only they can move from one atom to the other atom. That means they are participant in the transportation or in the conduction of the electricity. Now you can find different types of material. Some material you can find that these two bands, valence band or conduction band, will overlap. And some material you can find these two have some finite gap, means gap is less than, Eg is around less than 3 point of the order of, I'm giving 3.5 electron. Another material should have the higher than this value, higher than this value, greater than 3.5 eV. If these two bands overlap, that means electron is available in the conduction band always. This is metal. So in metal, no gap will be there. So all electron and hole will overlap. That means always in the conduction band, electron are available. But some material which have the gap is below 3.5 micron, by giving the temperature, electron hole pair can be generated. Electron hole pair can be generated. Hole pair. So some electrons should be available in the conduction band. So then it can participate in the transport. But if your band gap is very high, greater than 3.5, then electron cannot reach to the conduction band, even if you increase the temperature. So this means conduction band, no electron in the conduction band, no hole in the valence band. Always this conduction valence band should be filled. This is called the insulator. This is called the insulator. So in gap wise, you can consider that your band gap is low around 3.5, then electron can reach to the conduction band or it can create electron hole pair. But if the gap is higher, so even thermal energy to provide, the electron hole pair cannot be generated. So it should not participate in transportation. And this is insulator. Example, make the sand, SiO2. So this is the insulator. Other insulator, silicon nitride, silicon carbide, or aluminum oxide, those are the insulator. And those are below this one, so these are semiconductor that I give. Silicon is the prominent semiconductor, silicon, germanium, elemental semiconductor, or compound semiconductor, or gallium arsenide, aluminum gallium arsenide, other indium phosphide, and zinc oxide. These are the semiconductor group. There are several or band, which band gap is low, those are the semiconductor, which band gap is high, those are insulator. This is the physics of the formation of the band gap. So now I want to give you some example. If you want to this the electron hole pair, if you consider in the metal, number of electron is of the order of 10 to the power 23 per centimeter cube. This is the number of electron present in metal. But in case of the semiconductor, in case of the semiconductor, if you consider in case of the semiconductor, number of atom in the semiconductor number of atom is very less. Here, if you silicon, this atom at room temperature, at the rate of room temperature, how many electrons should be there? In silicon, number of electron at the conduction band on for silicon, number of atoms in the conduction band of the order of 10 to the power 10 per centimeter cube. This is the order of magnitude. For germanium, this magnitude is 10 to the power or 15 of the order of 10 to the power minus 3. For gallium arsenide, band gap is high, so this is of the order of 10 to the power 6 per centimeter. if you add this types of material 10 to the power 10 to the power 15, this number of electrons in this conduction, this is not sufficient for doing any electrical device. If you want to make any electrical device, this number of this carrier concentration in this level is very low, and this is not sufficient for making any types of transport device. So if you want to do some transport like the electron transport or whole transport or the charge carrier or transport of charge carrier through this, and you want to make some devices, this low number of electron, that is the resistivity is high of this material compared to the metal, where the order of electron is 10 to the power 23 per centimeter cube. Here number of electron is 10 to the 15, maybe germanium is the highest, other are the very low. The natural semiconductor other is very low, 10 to the power 10 to the 6, these are very low. So how you can improve the electrical conductivity in this material? So here, how you can make the impurity, increase the conductivity? With this, you can add some impurity. You can add some impurity in this layer to give some additional electron or hole. If you create some impurity level in silicon, if you add some phosphorus here, P, phosphorus in silicon, these are energy level of this phosphorus is very close to the conduction band of silicon. This order of magnitude, if I say around 45 millielectrovvolt. So here, if you want to create from the valence band electron, it needs 1.1 electrovol energy. But if your phosphorus is there, phosphorus have only energy difference 45 millielectrovol below the conduction band. So this can easily, this electron of the phosphorus can easily go to the conduction band, and number of electron in the conduction band should be higher at high temperature. So at room temperature, even that case, that very as per your replacement of silicon impurity level, the number of electron should be there in the conduction band. So you can increase this by giving the impurity which is close to the conduction band. We call this types of impurity, we call N-type impurity. N-type impurity. Or these types of replacement of the dopant, we also call its name as dopant. So N-type dopant. So this phosphorus in silicon is N dopant. Energy level of the phosphorus is close to the conduction band of the silicon. If you replace boron in case, the energy level of this boron in this should be closer to the valence band of the silicon. This is the boron level, this is the phosphorus level. So now you can check if its boron level is very close to, this is of the order of 42 millielectrovol above the valence band boron level. So electron from the valence band can reach to here, and here it can create the hole. So you can consider oppositely that boron gives some hole to this system. So if you add some boron impurity in silicon, then it will provide hole to the system. If you add phosphorus to the system, then it can add electron to the system. So two types of material you can create. Where one type is p-doping in silicon. So p-doping, this N-type doping in the silicon, it has higher electron in this conduction band level, You have higher electron in the conduction level than the hole. This is called N-type material. You have other type where you can dope it by boron. So this level is there, so it can create additional hole here. Can create additional hole here than the electron. So number of hole is here, positive charge is higher in the system, and then this is called the p-type material. P-type. Two types of material I consider, N-type material and P-type material. So here electron concentration is higher, electron concentration is higher in this part, electron concentration is higher here, hole concentration, positive charge concentration is higher. So this is called N P-type, this is N-type, this is P-type material. Now somehow you create these two types of material and you make the junction between this. You create these two types of material in reality. Now you create the junction between these two. Now you can consider junction between these two. Then what will happen? Here electron concentration is higher, here hole concentration is higher. So electron try to move to this side, hole try to move to this side if you have. So electron will reach from this side to this side and hole reach from this side to this side, and potential will change in the system, and this energy band diagram will now modify. In equilibrium. So it could modify the structure. So this is the where the potential will modify. This called the junction or depletion region. We call here all charges should accumulated depletion region. Depletion region. So these types of potential bending will occur under this system. So this is the real device structure, and here is the potential. The energy distribution in the valence band and conduction band should be something like this. So this is the N-type and B-type, P-type. This is the P-type. So this is the P-type system. P-type. So now this band I want to just remove, and just I want to draw it a bigger part. So I want to remove the band part. Just you consider the energy level is something like this. Is your device in equilibrium. This is N type and this is P type. This is under equilibrium. This will remain something like this. So electron is here and hole is here. If electron want to move from this, if electron in general conduction band, this is the lower energy, this is higher energy. For hole, this is the lower energy. For hole, this is the higher energy. So they try to move. If you want to now under equilibrium, you want to move this electron, you have to apply some potential. The battery, you have to connect this battery. This side negative part and this side for positive part, or reverse. Then you will get the current. And I will not go for the other part, the reverse part. This system will give some current. This is called the diode. This is called the diode. This is now the any PN diode, PN junction diode, semiconductor diode is behave like this. This is your characteristics. Current, and you apply the forward voltage. This type current. This is the first device. If you current, you add PN junction. We call PN junction. If here you not only this part, so you add another part. Let's assume NP. This is, you can consider PN, another P you add. Then you control somehow these two battery you can connect. In between one here, another in between these two, you can add up. So your diagram you can consider similar way, PN, NP. So your diagram should change to this way. Diagram should something like this. Energy diagram something like this. This is one junction This is another junction. This is N, this is P, this is P. So this called PNP transistor, because you have two junction, and these two junction can be controlled by two gate, two bias voltage, Let's assume VE, this is VC if I say. So you can vary this by keeping the characteristics. The input characteristic, first one, if you vary V versus current, input current, if you say this should be something like this, like a diode. If you now put the output, this current, if you want to measure this current, if I say this is IC, this is IC. So if you want to IC versus DC, it would vary something like this. So this is zero current, we call off, and this is high current, we call on state. This is the first device as a transistor. Whatever in the computer you are using, whatever the information you write, A, B, C, D, 1, 2, 3, this is 0. Initially, if you give some information, it will go to the on state. 0, you give some current, so it's on state. So your data is stored 0 to 1. This is 0 and this is 1 state. Off on state. So transistor is something like this. So PNP, or you can modify something NPN. So for simplicity, for one day class, I am giving you the information. PNP transistor. So this is your first device which can switch on. It can transfer your information. So it is the on and off state. This is the situation. Any information you are giving. Now it is modified of this version BJT. It can high power consuming, bigger size. So heat generation will be there for the bigger size, etc. So modified part of the device. If I say one type, simplest I want to say FET, and this is one type of FET I want to device. Nowadays we are still using the MOSFET. Its full name is metal oxide semiconductor field effect transistor. This is another types of transistor, MOSFET. If you want to just explain simply the diagram, how it's look like, if I say in cross-sectional view, this is maybe considered P-type material. Then you dope it by N-type. You dope it by N-type. Okay? 3D you can draw this. This is 3D you can draw this. So this is the doping area. This is the doping area you can. And top of that, you can have some SiO2, silicon oxide, SiO2. It is semiconductor band gap insulator. This SiO2 band gap I wrote is a 9.1 electrovolt, huge band gap. So no transport of electron can possible because of this insulator. Then top of that, this is the insulating part which should have along this direction. So this is SiO2 pre-made, and then you give some metal on top of that. You put it with metal. This is the metal oxide semiconductor. So that's why it's called metal oxide semiconductor. So under field here some electron can be accommodated, and if you apply some bias between this one to this region, N type, N plus, this we call source type, source, SOURC. This is called the drain. This is drain. And from here to here, electron can transfer source to drain by controlling this part we call gate. This metal part we call the gate. You can apply the bias between the gate and source and drain. So if you apply the bias, and you can get the characteristics of the gate bias VG and get the current, drain current. So you can see similar types of characteristics, 0 and high current. This is on state, this is off state. And this side, this is the very important device. Same as it's also transistor, but it's had consumed less voltage, less current, and so this will produce less heat during this part. So this is the one type of transistor you can make. This is called MOSFET. And nowadays, most of your laptop use these types of transistor where you are storing the data. This length this length of source to drain we call channel length, or we call also node. So earlier in 1980s, the size of this channel should be few micrometer, even 100 micrometer, this length. So it's a very big size transistor was there. But if you have bigger size transistor, same current is flowing to this. That means your heat production due to this bigger size resistance is high. So your big heat production is very high. So when you run your computer, laptop, etc., its heating is coming from the system because of this current flow through the material, and this heating is very huge. If you means this is your maybe the chip size, total number of transistor is there. Now the whatever the heat is producing, and if you make this small, let's assume this number of, let's assume you use 1, 2, 3, 4, 5, 6, 7, 8 transistor. Whatever the heat is producing, if you make its smaller number of transistors, you increase this, same amount of heat will be produced, because the resistance area, total area of resistance or total resistance of the system is almost same. So if you increase the transistor, same heat will be produced. So it's miniaturization of the transistor is very required, and from this few micrometer, now you can 1 terabyte, 2 terabyte, you are thinking you have the data storage devices, something like that, and that is because of the miniaturization of this transistor size. So this length, now node size, now the last year my laptop had this node size of 10 nanometer. 10 nanometer means 10 to the minus 9 meter, and 1 micro 10 to minus 6 thousandths time lower than that. So this is the 10 nanometer size, and I know that nowadays even the 2020 the transistor made of 5 nanometer node, 5 nanometer nodes, and there on the next only target was 3 nanometer node. That is the last target. Within couple of years it should be in. So classical way we are in decreasing the size of this transistor will end, and you cannot make new types of modification in the classical way. So you need new types of technology. That one of this, the qubit quantum technology is coming. This is in the format quantum technology. That is the future. That is the future. So in couple of years, the reduction of the size by classical process, this on-off state, this types of transistor will end, and you have to see new types of modification. Your speed of the computer will not further increase as per the classical way. So new types of technology is coming. One is how to make one of the solid state. There are several but one of the solid state types of device, if I solid state type means solid material based devices, the solid state based qubits or spintronics device are there. So one of the transistor, if I say SET, single electron transistor, it's called single electron transistor. This is very important tool for the study of quantum technology, single electron transistor. So if I draw the MOSFET along this, if you draw the energy characteristics, potential diagram in the conduction band, this is the diagram. And the valence band, same thing like this. So I don't want to focus on the electron transport. So valence band, you don't need to think. This is the conduction band. This is transport. This is the flowing process. Then by gate, applying this the top metal gate, you can reduce this barrier. And earlier electron have to cross this barrier, so low current, and after that you have to get higher current. So something tentatively I'm drawing this way. So otherwise you can also draw simplicity. So if this barrier is low, then electron can cross this barrier, current should increase in this case. Get voltage type characteristics, will get this type. This is barrier. This type of part is called barrier, and this height is called the barrier. Potential barrier or potential barrier. ACT is made of two types of potential barrier. If you create something, there's two types of potential barrier. This is your electron reservoir. Huge electron is there, electron reservoir. So this is the potential, chemical potential of the system. The electron fill up to this. You have some electron up to this. You give some barrier. Just I'm giving the future, so that's why I'm just giving some introduction of the system. If we give some barrier difference between this chemical potential of the source, something like this, chemical potential of the drain is deep. Now you can see you have double barrier structure. This barrier structure, double barrier structure. So this is barrier 1 and this barrier have in general only resistance. It have resistance and capacitance effect. Resistance and capacity. If this resistance, if somehow is greater than, if this resistance of this junction is greater than 25.8 10 to the 6 kilo ohm, this two, then if two electron want to go to here, if one electron is there and another electron want to come here, then this electron can stop the other electron to come. This electron, if one electron is in this region area, and if one electron want to enter from any of this side, it cannot able to enter unless you can give additional energy. That is the phenomena is called Coulomb blockade. Coulomb blockade. This phenomena is called Coulomb blockade. If one electron is there, next electron cannot come, and you have to provide some energy. If I say this is ECH energy, it's called the charging energy. Charging energy. Charging energy. This amount of energy you have to provide to enter another electron. This is the part that at a time only one electron can enter to the system and it can go to the outside. So your current level, if you plot the current along this I versus VD, I versus VG gate voltage, you can see these types of current. Current peak if you get. And this separation is your ECH energy separation, ECH. And more complex. This is the current of ACT. A time electron can go. This is the one of the main instrument nowadays can be useful for to detect the single electron, and it's called single electron transistor. And this tool, this single electron transistor, can be a sensor for various applications. For the quantum bit, for the other types of quantum sensor, this ACT, single electron transistor, can be very much useful. So I am one of the expert of ACT. So not only this ACT, we are making from our lab, and we are making the device based on this ACT. This part, whatever we are focusing, this part we only use the inner oil. This oil, potential oil, we are creating by using a single atom. So this potential types of barrier we are creating by using a potential of a single atom, and this single atom called single atom transistor. This is the important part, and I am one of the person who can make the room temperature. The single electron transistor mostly work at very low temperature. Low temperature, but few are able to do it. And for atomic group, single atom or few atom group, I created three atom cluster, three atoms cluster, which can work, which can operate. If you increase the temperature, what will look like this one? This is at 1 Kelvin temperature. In 10 Kelvin, this will be something like this. This characteristic will burn. If we increase the temperature, this characteristic look like this. If you go for 50 Kelvin, this should be. And higher, if you 100 Kelvin, you can get flat current information of ACT. So if you want to get the information of ACT, this ECH should be very, very high, at least 200 millielectron. Otherwise, you cannot see this current in high temperature. So I make some device with 3 atoms, and that will work. And sustain their ACT current at room temperature. This is data at room temperature, and low temperature data is 5 Kelvin data. It's 5 Kelvin data. This is 300 Kelvin data. So our lab are focusing on to make the single atom transistor which can give room temperature data, these types of device at room temperature. This should be the ACT at room. That is our target. We are working on this direction, and to get room temperature. This is our data, and now we're focusing these types of single atom transistor, single electron transistor at room temperature. We're focusing, and this ACT is very important. Room temperature or single electron transistor, single atom transistor can be used for quantum bit or qubit. The data showing 0, 1, what I say we call 1 bit. So this quantum technology we can use. This one we want to make other quantum sensor, single electron current metrology. We can say single electron current metrology. So high precision measurement of the current metrology. We are working on this. We are working for using this system. We want to single photon detector. Or quantum bit. 2 types we are working on. One is charge-based qubit, another is spin-based, electronic spin-based, spintronic spin-based. 2 types. Short system to create qubit in high temperature. High temperature qubit we are focusing on. High temperature qubit. This is our target. So this is tentatively I give you some information what research going on at present. At present research is going on ACT, single electron on transistor, quantum bit, single current metrology, single photon detector, or voltage metrology, current metrology, resistance metrology, capacitor metrology, all are in quantum range, single photon detection, phase metrology, etc. These are the solid state based system. These are the research going on, and the classical result is up to this MOSFET. You can consider this MOSFET features what I explained you. This MOSFET is now the classical. So we can explain this is the classical in maybe analog electronic system. I teach up to this part MOSFET and how it's work. And the future you can change from MOSFET. You can go to the single atom transistor, single electron transistor, and to the so on small atom system, and you can make several types of device which can be the quantum sensor, quantum technology for the future of quantum technology. So I give you the basic concept of semiconductor insulated metal, starting from the atom atom nature, and then how you can apply this the semiconductor to make some basic junction. It's called the PN junction or diode, then diode to transistor, and transistor to MOS types of FET, and MOSFET now modified this MOSFET to the single electron transistor. Single electron transistor key tool for all types of most of the solid state based quantum technology. It could be for the superconducting qubit, it could be the solid state bit qubit, or 2D electron gas system based qubit, or the atom based qubit. So all is required. Means most of the solid state bit, unless it is based on the photonic. Even in this case, whatever I'm showing you here, we have the atom energy level, and that can be coupled to the photon. So photon interaction, photon based system and the solid state based system even can be coupled to this part. for the future electron communication system. So for future quantum communication system plus quantum devices, all is required. So this is the future of the. I started from the basic and how the semiconductor is formed and how that basic device is the classical device is working and how the new types of technology is upcoming, and those upcoming electron technology, solid state technology is the quantum based on the quantum technology, and it's the next 20-30 years we'll work on that to develop such quantum technology. And a few of our department faculty is working on, but mainly the quantum ACT based system and their quantum technology. I'm one of the expert who can make the devices and the material tool for such purpose in the department. So if you have any queries, you can ask me. So related to that.
Excuse me, sir. How are we
little louder?
How are we getting those SAT characteristic at room temperature?
That's I say the important thing, the ECH charging energy. If you have the higher charging energy, then only you can able to get the characteristics that survive at high temperature. The minimum requirement is 200 millielectrovolt. That should be the charging energy. Room temperature energy is 25.6 around 6 millielectrovolt. So it's 200, and this creation is very difficult. To create such thing, you have to go for the size of the quantum dot. If we say the smaller size, that should be of the order of 2 nanometer. And this creation is really difficult.
Okay, sir.
So you have to be expert how to create such gap. That's the two important thing I want to say. That I draw here. This is a potential barrier. This barrier should be very high, 300 millielectrovolt. One, and the charging energy. That is another concept. The Coulomb interaction. That the separation. This one should also be very high. In general, it is around mostly it is a few millielectrovolt, 10-20 millielectrovolt. Okay, my device, this device, I say this is 100 millielectrovolt device. That's why still it survived 4 times higher than room temperature, and we want to make 200 millielectrovolt that will sustain. And this is very critical. That's why we are doing the research.
So we basically need more resistance to control the atoms.
No, if you increase the resistance, then your current should be low. This current value should be low. That's also a problem.
Okay, sir.
It's
But
the
then
balancing, it's the optimization process. If you increase the resistance, current should be low. This current peak intensity should go to the, now maybe it's the nanoampere level or microampere is better for this operation process. Nanoampere, if you go increase the resistance, then this will go to picoampere. Your detection, you can in the range of the noise level.
okay, sir.
It's the expertise. You need to play with so many things. It's with some of the resistance is important, capacitance are there, those are important, barrier height is important, and the other issues is there. So we are facing several important questions that you have to play with to get the good device for room temperature.
Okay, sir. Understood. Thank you.
Anyone do any other student have any queries?
Sir, how can we increase the width of these potential barriers?
Width, if you create, there are several ways to create the potential width. That is the width you can take. One is the width, another is the height. Two important part is there. So that the potential barrier I create this one, this the width. This width your size, real size of the in between the quantum dot. This is the important. You place a quantum dot and give the gap. That is the width. But how to create this barrier, it's a different issue.
Sir, like even at a high temperature, we increase the width of this, then the quantum tunneling will means reduce substantially. So then
it will because two way. You have to the some tunneling percentage should be there. So if your that gamma, two factor is there, one is the resistance and one is the tunneling. If you increase the width too high, then you know that the tunneling probability that is depend on the width. So probability will reduce.
So then we would be able to means do the same experiment at higher temperature, right, sir? Means like we will cancel out the height factor with the width one actually means.
That the, as I say, resistance is the one important thing. Another important thing is the this part, the capacitance. So there is a capacitance between these two. This tunnel capacitance should also be very low. Its requirement is auto farad. Tunnel capacitor requirements is the auto farad range to get the charging energy. ECH is the charging energy is E square by capacitance, source capacitance, gate capacitance plus the drain capacitance. This is the charging energy. So capacitance should be low. To make the capacitance low, your size of the this part should be very low. And capacitance formula in general, if you consider parallel plate, epsilon A by D. So if you D is increased, D, this you are talking about this D. If D is higher, capacitance should be high. The high capacitance reduces the charging energy. So it will work in low temperature.
Okay, sir.
So there are several issues are there. So we have to play with. We are playing with. I know how to do it. So I already did, and we are working. We are establishing the whole capacity facility. Okay, that is the important. Hope within this year we hopefully establish the full facility. Then only we'll work on to fabricate again. So that those issues. There are so many physics is involved in this case, and that we are playing with. That's why we are doing the research, and we want to lead this field from India. The atom based single atom based devices for room temperature. Few group are working in the quantum dot based system in India now and getting project, but I am the only one. Another professor is there, but he leave that field. He now moved to the quantum dot based system. He is in IIT Bombay. But the dopant based system, or means individual impurity based ACT or the quantum device, the two person in India have only have expertise. One is myself, another one is Professor Sudha Sattu Mahapatra in IIT Bombay. Now he is working in the quantum dot system due to that the inability of the facility related to the impurity level, means single atom based device. So we are establishing this. We already get all this budget, and now we are going to just purchasing procedure and the procedure in under process. So these are very important future directions. So we are looking for to develop the various types of quantum sensor.
Okay, sir.
So anyone have any other queries? If you don't have any other queries, I want to stop, and maybe I try to share this lectures. If I have some recording, I try to save it. So okay, so best wishes from my side, and if you have any queries, you can email me. Okay.
Thank you, sir.
Thank you, sir.